Now, some of you asked about software already, so this is great. We're going to be coding in a dialect of Lisp that's called Scheme, originally developed at MIT. There's an IDE for this called Racket by the PLT group from Rice. It's a very nice IDE, and it's a nice language. We'll be doing it as our algorithmic calculus, and I'm going to sort of justify that to you and tell you why we're doing it that way. It's a functional programming language, which I think is pretty interesting. So let me mention that Duke is a small CS department, although there are a lot of really excellent people at Duke. And I want you to be prepared to some extent for going out into the world. So let me mention that at Cornell, at Carnegie Mellon, at Stanford, there's a required course on functional programming. And this is heavily emphasized. This is the only class at Duke in any department that teaches functional programming. And you'll learn what that is. So it's a very important paradigm, both practically and mathematically. It's very close to the mathematics. And that's one reason why we use it. So we'll talk more about that a little bit later, but that's the reason that we do things in this way. And more will become apparent. Moving on, there'll be lecture notes. I'm going to try to have them up beforehand so that you can have them for these lectures, but they might come up afterwards. So let me tell you a little bit about how this course is sort of situated. So this is really a general introduction to mathematical computer science, by which I mean the mathematical study of computational problems. And the main prerequisite isn't all these courses you see, it's the ability and willingness to work hard and try to think clearly about problems. So the theme of the class is think a lot, write a little. Doesn't have huge programming assignments, you write a little bit having thought a lot. And I don't think it helps to have a lot of programming experience. In fact, it usually doesn't help because you developed some habits that are different from this class. So what we usually want is for you to have some amount of what we call mathematical sophistication. You've seen an engineering math class, you've taken calculus. In terms of actual math, you should be able to do algebra. We're going to use examples that have integrals and derivatives. We don't really use calculus per se. The best preparation really is high school geometry, which is last time most people here did a lot of proofs. I know there's some fancy people who've taken a proof-based linear algebra class and so forth, or analysis, but it's unusual in this class. So we're actually going to prove things. How can we mathematically prove things about programs? And as you can see from the title of the class, Discrete Math for Computer Science, this is in some sense an old school mathematics class. So there's lots of math, but it's also a CS class, so we're doing some programming to reify and instantiate the mathematical concepts, but it's not a programming class per se. So we're going to cover how to reason about computational problems clearly, what's the mathematical basis of functional programming, higher order functions, recursion, and so forth. Formal skills, again, proving properties about your programs, specifications and contracts, what's a formal model of computation, and why do we do this? Well, most software is broken. I mean, look at voting machine software. This is terrible, right? Formal tools give you good basis to avoid problems like this. So this is a historic problem. Software being broken and formal mathematical tools can help here. So there was a Mars probe not too long ago that crashed because there was two parts of the code used different conventions for measurements. One used metric, one used English. Your parents can tell you about the Y2K problem. Old code lasts a long time. Namely, you had to update programs which assumed that years couldn't be higher than 99. There are hundreds or thousands of exploitable software errors for hackers and phishing and malware. At the Denver airport, when they made it automated with robots, the robots threw the baggage around, hitting passengers with it, causing a lot of injury at first. I'm all for universal healthcare, but the original rollout of healthcare.gov had many bugs. And of course, there have been rockets in Soviet Union, former Soviet Union, and current Russia, and in Europe that have blown up because of errors in the coding for the LOX flow. So the style of the course tends to be what I would call kind of mind-bending. There are lots of new concepts, like treating functions just as if they were data. We'll do some fun things. We'll implement RSA cryptography, which is behind your credit card, finite automata. A lot of the learning is in the problem sets. most students enjoy the problem sets. We're going to discuss the discrete mathematics of functional programming. So the MapReduce model, which is mathematically interesting, now widely used at Facebook, Google, Microsoft, Yahoo, etc. There's lots of work in the class, so be prepared to put in some time, but quality time. Don't just hack at the problem. You have to think clearly and then write your code or write your solution. And we try to have some fun. There's examples of extending problems and so forth. Okay, what about philosophy of the class? So this course, for many of you, will introduce the deep mathematics in computer science. So in some sense, this is an introduction to some of what might be called higher mathematics, but all related to computing. But the term computer science is kind of a strange term in a way, right? I mean, actually, I think it's sort of a terrible name in some ways. So it's not really about either one, computer science in some ways. So it's not about computers per se, right? They're just our tools. Like we don't call surgery scalpel science, we don't call math arithmetic science. So that's not such a great term here. And also, I don't think what we do is a science, right? I mean, there's poultry science, there's military science. You know, any discipline that has science in its name probably isn't. I was very opposed when biology department renamed itself to be biological sciences. You don't see biochemistry renaming itself to be biochemistry sciences. So this is not such a great term in some sense. I don't think this is really, it's a legacy name. So I really think computer science is really more some combination of three things: mathematics, engineering, and some kind of design or expressive art. So we're going to try to get at that through mathematics. We're going to emphasize mathematics while making a lot of connections to engineering here. Now, as we edge into content, I want to say that the names of disciplines are very misleading in general. So it's one example. Geometry. I mean, I'm sort of trained as a geometer, as a mathematician. So this comes from the Greek geometra, or geometry, meaning earth measure. So basically the story here is that in Egypt, the priesthood was charged with restoring boundaries of fields, roads, and so forth after the annual floods. Floods were necessary for irrigation and for fertilization. They sweep away all the boundary markers. So they had to invent square roots and all sorts of things for dealing with triangles and rectangles. And they basically invented geometry more or less to handle the angles and distances and so forth and areas. And they almost got it right, kept Egypt running for a really long time. But today geometers, they're mostly not measuring the earth, right? They're working on other things, and the main contribution of geometry was formalizing the notion of space. So similarly in this class, we're using tools, maybe computers, DNA, RNA, quantum qubits, things like that. We're going to do our computation. There are tools, but our most lasting work is going to be formalizing notions of computation, understanding what it really means to compute. So there are lots of topics listed on the course webpage, but I wanted to give you a little map of what we're doing, and it's in text here, but I have a little better drawing that I want to show you in order to kind of give you an idea of the first few weeks of the class at any rate. So you might think we're going to go through this sequentially. We're not, but I want to tell you kind of what I have in mind here. So in a math class like this about computational themes, so discrete mathematics relevant to computer science, there are some things that I want to get to, and anyone wants to get to, that are fundamental topics here. And so let's number them a little bit. Let's just talk about it. We would like to get to the heart of a discrete math class is really iteration, recursion, and induction. And let's make that in red so we can see it. So that's really fundamental. And then, of course, I want to show you something deep. I want to show you Alan Turing's halting theorem. So let's call that one also. And let's try to write that a little bit better. So these are things we have to get to in a discrete math class. Now, in order to do that, I have to teach you something about the logic of programming. Like, what do programs mean in some sense? And related to the halting problem is Alonzo Church's Lambda Calculus. So I want to teach you the Lambda Calculus so we know really what our programs mean. And that immediately gives us a model for what the expressions mean in a language. So we can reduce expressions to value. That's called the substitution model. And it gives us an instantiation in an actual programming language called scheme. That's pretty exciting. So all of a sudden we can do things in a language and we can have mathematics that tells us what it means. And with these things in place, all of a sudden we have a rigorous basis for proving things about order of growth, asymptotic complexity, and we can do some interesting assignments, a little bit of number theory, RSA, cryptography, graph theory, finite automata. And then we could do some other things. We could talk about the mathematics of functional programming, like what does it mean to have a functional program? And we can then do something more applied. We can talk about the revolutionary technique for cluster and cloud computing called MapReduce and Hadoop, now operationalized by Google and used widely in cloud computing. I'll talk about that a little bit. It's number 7. And we'll also be able to ground this by telling you some about how to do proofs and how mathematical logic works. So those are sort of the themes, and the numbers aren't the order, but they're the dependence. Given that you want 1, you have to have 2. Given that you have 2, you have to have 3, and so forth. So that's really some of the topics we're going to cover in the class, grounding this in mathematical computer science to actually do some quite interesting practical things. Okay. Now, let's go back to where we were before. Okay, so continue a little bit. Why is this useful, right? So obviously it's math, why is it useful? So we think this discrete mathematics is going to help your skills in reasoning about what we call computational processes. This is kind of the key thing we want to emphasize in the class. So we're going to write some programs, but the goal is to learn the mathematical basis for our bag of tricks, functional programming, higher order functions, and so forth. We want to understand programs. So correctness, is your program correct? How much time and space does it take? And better problem solving. Can we do this faster and more accurately? So basically what you should get out of this is that a little bit of thinking is worth a lot of coding. So don't hack, instead think. And I have a little parable here. I'll let you read on your own, and we'll come down here. So the key thing, and this may be apparent to some, but not others. So this course and later courses and what computer scientists do in general are not programming classes mostly, right? Programming is a basic tool. You know, mathematicians don't spend all their time solving calculus problems. And in fact, there are no professors of calculus, right? They're professors of topology, algebra, numerical analysis, number theory, algebraic geometry, geometric algebra. Calculus is this tool. All mathematicians know calculus, and they can solve calculus problems when they run into them. Similarly, we have a distinction between what we're doing and what you might call pure math. So these computational processes, which I want to be fairly precise about, so these things aren't quite mathematics. So computational process encodes algorithmic knowledge, right? Like how to do something, imperative knowledge. And mathematics encodes declarative knowledge, like what is true. And so our goal is to develop rigor, computational rigor, precise descriptions of how to compute something and how to go back and forth between these two things. So let me give you an example. And these examples will be very easy in the beginning, but if you are wondering if this is too easy, the class will accelerate some starting with next lecture, but I want to kind of bring everyone along here. So let's think about something like square root, like mathematically. So here's some declarative knowledge for how we think of the square root function. So declarative knowledge says square root is the unique y such that y squared equals x and y is non-negative. So this defines square root, at least for some x's being numbers or matrices or things like that. And with some mathematics, you can actually prove that it's unique, namely if there are any y's like this, there's only one of them. So we can tell, for example, that the square root of 9 is equal to 3, for example, and we can check it from the definition, and that's great. But this doesn't tell you how to find the square root of some number x. You could just check it, right? And so how would you actually compute the square root of x? Well, you could try all possible ones, compute y squared, check if it's x. This could take a really long time. It's a terrible algorithm. It certainly doesn't work for things like real numbers very well. So this is kind of an issue. And so one way we could develop an algorithm to think about this is we could start with a mathematical observation and try to turn this into an algorithm. And so I want to start with this observation here. If g is greater than the square root of x, then x over g is less than the square root of x, and conversely. It's pretty interesting. And let's see if we can turn this into something that relates to our algorithm. So for this, let's go over to the document camera. Look at our proposition here. So one of the things we could do in this class is when we want to understand things, we can try to prove them. So we've observed let's see, I wanted to we've claimed that if g is greater than square root of x, then x over g is less than square root of x. So this interesting statement, it looks plausible. Let's try to prove it. That's kind of what this class is all about. So our first proof of this class, let's look at this. Suppose we were to say, take the first case, g is greater than square root of x. Well, if this is true, then we can take reciprocals, so 1 over g is less than 1 over square root of x. That looks good. Now we can multiply both sides by x, x over g. That, watch me like a hawk. Thank you. Appreciate it. So it wasn't a proof, but now it is. So now we have an argument for why this is true. So when we consider this, I want to sort of come back to this, and this will be our attempt to, thank you. This will be our attempt to understand the nature of how we make these arguments. When we look at this, I think the steps seem pretty clear, but that's really something for you to tell me. Do you believe the steps? And do I need to prove them more? But when we look at this first step here, here's one thing that does seem intuitively plausible, right? This seems like a very decent step, but someone could question whether or not that's true. So if we were a small group, I would say, do you believe this? And I'd ask you if it was true. And if someone wanted me to prove it, then I would try to prove it. So let's write down how we would do that. Let's say, why? Why is that true? Well, let's write a little claim to see if we can prove it. So we'll say for all AB greater than 0, this is a mathematical symbol pronounced for all, for those who haven't seen it. If A is greater than B, then 1 over A is less than 1 over B. So what I'd like to do, just to get in the, this is relatively straightforward, just to get in the habit of having some conversations and interactions about our work, what I'd like to do is come back to this just a little later, but before the class ends, I'll ask for your ideas on proving this, and you can tell me your thoughts, and then I'll either use one of your ideas or one of mine, and we'll end up proving this. Okay, good. I want to go back to going from the lecture notes now, and we'll come back to doing some writing of mathematics later. Okay, so I greatly appreciate the feedback and also catching typos. This is really great. It's what mathematics should be. And I wanted to come back to our attempt to understand where we were in this algorithm. All right. So this is sort of a paradigm for mathematical computer science, namely, we can make some mathematical observation that gives us an entree into how to solve a problem. And we can use that to come up with this iterative algorithm you see here to find square root, or rather a pretty good approximation to it. This is actually a pretty cool algorithm. It's one of the first algorithms ever described. It was done by Heron of Alexandria. He was one of those guys in Egypt, namely Alexandria, who was charged with understanding mathematics to redraw the boundaries. And they needed square roots. So basically, you could think of it this way. I'm not going to use very much pseudocode in this class because Scheme is our algorithmic language, but we'll use it here because we don't know very much Scheme yet. So the algorithm would be make a guess. Suppose you want to find the square root of x, non-negative guess, and then improve the guess by averaging x and x over g, and stop when that guess is good enough. Like this is a little hard to read, so stop when the guess g squared minus x absolute value is small. So it's an iterative algorithm, converges pretty quickly. Now, we know this historically. It's pretty interesting that Heron developed this. Later, Newton came along as an Isaac Newton, and he generalized this to cover almost everything. So now it's called Newton's method, but for square roots, it was Heron's method. So here's a little trace of how this works. It works really well. So we take x, we want to get the square root of it. Let's guess 1. Why not guess 1? X over g is 2. So you can imagine g get the new guess is 3/2 or 1.5. And x over g is 4/3. So the new guess is 17/12. X over g then is 24/17. And so the new guess is this thing here, which is off by about 1 part in 1 million. So kind of a nice algorithm. It's based on this key mathematical observation that we observed and then proved here. So that's kind of a way to think about how we're going to try to approach developing algorithms in computer science in general. All right. And I'll code this up for you. Well, it's already on the web. It'll be in lecture notes for 2, and we'll go through the code to make sure we understand how to do this. So the key thing is, I would say this. There's a distinction between declarative and algorithmic knowledge. So declarative is a description of what it does. Algorithmic knowledge is a description of how it does it. So in some sense, declarative knowledge is more like math. Algorithmic knowledge is more like computer science. So we need to have both of these things to have a good understanding. So I know some of you have experience programming, and you probably know from experience that going from what to how is not always easy. And going in this direction, this is really what being a good programmer is all about. But it's also not always easy to go from how to what in this direction. The how can be really detailed, and it doesn't necessarily reveal the what in a straightforward manner. And our goal is to teach you more about moving back and forth between the what and the how using mathematics. Okay. Now, a key mathematical idea in CS, and we'll see more of this, is abstraction, which I'm sure you've heard about in 100 or 201 or something. So we take a computational process, we give it a name, standard interface, we put it in a box. So we define a box called square root, and we put x into it, and we get square root of x out. And we can use this in any place we want. So this is something that we want to do. We want to be able to define these things too. The analogy for this would be, when you're hooking up, if any of you are musicians and you play music that needs to be amplified, there are a zillion connectors and Bluetooth devices and so forth, USB, lots of different kinds of boxes. You can have the same kind of cables and connections, and you hook them up any way you like. So this is a nice metaphor for how we're going to do things. Now, in order to proceed to do this, we need to have a notion to tell the computer what to do. So we chose Scheme language with some extensions provided by Swindle here. Look at the handouts for today. We're going to cover more in the next couple of lectures, and then in some sense you'll know the whole thing. Now, this is a kind of white lie. Like I could teach you the moves in chess in a half hour, but take you a long time to be a good chess player. But Scheme has a very simple uniform syntax, whereas some languages are almost all syntax. And after a semester, you'll be an expert, and you'll know how to use a functional programming language. So it's a really interesting language, and it's quite close to Alonzo Church's Lambda Calculus. So let's talk some about that a little bit. So the everyone knows Alan Turing, at least the name, but Alonzo Church invented the Lambda Calculus. Lambda is written like this, just like a fraternity of computer scientists. So we're going to spend some time learning this. It's the logic of computing in some sense. And so what I would say to you, that this gives meaning to our programs. So my view is that the real contribution of Newton to the physical sciences was developing a calculus, a way to talk about the mathematics behind the physics. So Lambda Calculus is to computing as Newton's calculus is to the physical sciences. So the Lambda Calculus and the Substitution Model and the proofs, that's a huge part of discrete mathematics. It's the foundation of functional programming. So in some sense, if you have a program that is iterating over something or recursing over something, induction is going to tell you that everything with the numbers are going to add up correctly. And the Lambda Calculus is going to tell you that the meaning of the statements in your program are what you think they are. And this is what resulted in the MapReduce model, which is basically the functional programming model that made it possible to use hundreds, thousands, even millions of processors together with a very simple interface, and one that you'll know cold by lecture 12 in some sense. So let's begin, talk about this a little bit, and we'll come back to our problem. So let's think about this Lambda Calculus, which is a branch of mathematics as embodied in scheme. It's a good operational model for the Lambda Calculus. So scheme is sometimes described as prefixed ordered fully parenthesized. Basically, it looks like this. The operation to perform always comes first, and every part of the program has parentheses around it. So there's a bunch of effects. So one is the syntax is super simple. You never have any question about what expressions mean. And whenever you write something, you put the operator first. So it's a little strange at first, a little alien. Is it just like Pascal or just like Java or just like C++? It's a little different, but there are advantages to this. So for example, if you look at this expression in Java here, it's ambiguous unless you know the precedence rules. You have to memorize stuff. In scheme, the corresponding expression is this. It's never ambiguous. So there's no ambiguity in things like this. Here's another one from Java. We have this guy here, this nested test here. You know, I don't want to put you on the spot, but generally if we ask students what happens here, some know it and some don't. Does the else go with the inner if or the outer if? Again, you have to know the rule. It always goes with the innermost, right? But unless you know the rule, you don't know what happens. You have to carry this around in your head. So again, this is pretty interesting because we have an unambiguous, simple semantics and syntax. And the way you can always unconfuse yourself is to remember the following. Everything in scheme is an expression, which means it has a value. So the value of +4 times 5(2) is 14. So everything in scheme is an expression, and every expression has a value. All right. So what do these things mean as we're starting to write code? So an expression, and this is an example of expression, it's one of two things. It's either a primitive or a combination. Primitive is a thing like 1 minus 31 plus any of these things. Combinations are a bunch of things, one or more expressions enclosed in parentheses. So here are examples of expressions. +3, 5, that tells it to add 3 and 5. This expression here says take the GCD of what? What happens when you, 59 and 6. GCD is a built-in scheme function. So the order of expressions in an operator is always as follows. First thing is the operand. First thing is the operator, sorry. Everything else is an operand. So this is the thing to do, and these are the things to do it to. And you can see that in these examples here. Plus is the thing that's done to all this stuff. GCD is done to these things here. So operator first, then operands like this. So one of the things is that the definition of expression actually is recursive. So a combination is one or more expressions, but an expression is defined here. So we have to develop some comfort in thinking recursively. All right. So for almost all operators, the value of one of these combinations is determined by a very simple rule. And this in mathematics is either called alpha renaming or beta reduction. You don't need to know those names. Part of the substitution model, there are 2 steps. And this is a very baby introduction. This is called eval, and this is called apply. So the first step is evaluate the sub-expressions. Note the recursion. To evaluate, we have to evaluate. And then we do the specified operation, which is the value of the first expression, to the operands, which are the remaining expressions. So let's look at our example here, times plus 3, 4, 2. First, we evaluate star, and it comes out, it's bound to, it comes out as the procedure multiply. And then we evaluate plus 3, 4. Now we recurse. To evaluate plus 3, 4, we evaluate plus, we get the primitive procedure add. 3 is 3, 4 evaluates to 4. Now finally, we can do it. I do the apply step, i.e. applied the specified operation to the operands. We actually add 3, 4 to get 7. So this is now 7. You can see the substitution coming in here. Now we evaluate the 2, and it's 2. Finally, we can multiply 7 by 2, and we're going to get 14. We'll go into more detail about this before. Everything is done inside out. All right. So this isn't very exciting. We have arithmetic so far. But the key thing is that this rules apply to almost every function in Scheme, except those that are called special forms, and there are almost none of these. Let me point out that in most languages you've seen, almost everything is a special form. So there is a need to write special rules and memorize them. So this idea of reducing expressions to value, this is sometimes called semantics. And in many graduate programs, there are multiple courses in this, although we only have one person doing this at Duke, Professor Ben Rossman. So the way we get power out of this is by naming things, and of course you can define things. So we want to have a name like square root of x, not the unique y such that y squared is equal to x and so forth. So it sounds trivial, but getting the name right, this is a huge part of engineering. So think about it. So we can define global variables in Scheme like this. We can define a variable called data, which is equal to 13 in this case. We can also, everything is first class, so we can define a procedure called add up to be whatever plus would be, and now we can use this. Here what we do is we take data, which is 13, add up, which is plus, we can add these, and wharf will be 15. So in general, this special form for define, for naming things, which is really important, has the form define, name, expression. And this is why it has to be a special form. We can't evaluate this using the rule before because you have to go through and evaluate each sub-expression. Maybe define has some meaning, but name is undefined or it has some other meaning. So we had to have a special rule for this. But there aren't special forms in great numbers in Scheme. There are only a few. And then you'll be done and everything else has these main points. So I've allowed some time for questions. I'm going to sum up, but I want to come back to our attempt to do a little proof and maybe have you all help me with it. So let me come out of here, stop sharing the screen. Would someone like to give any advice on how we could do this proof? Well, how would we know this is true? How would we complete this proof? What do you think?
Maybe pick 2 numbers.
We could definitely pick 2 numbers. So that's an interesting idea. So if we did that and we found that for the 2 numbers that in fact it didn't work, right, then we would have falsified the claim, right? But it would be very difficult to have a proof that worked for all numbers. So I think that what you've described is a good way to get a feeling about this. I see a suggestion from Moses suggesting a proof by contradiction. And I rather like that idea. So let me set that up and see what we can do. So proof by picking numbers is good to get a feeling for what things look like, but a proof by contradiction might give us something that works for everything. So proof by contradiction, we assume the opposite and see if we can derive something that contradicts reality, get a false conclusion. So let's try Moses' suggestion. Proof, let's say, by contradiction. And if we're lucky, we can complete this without my knocking anything down or breaking anything. That would be really great. All right. So when we do a proof by contradiction, we want to say something like, well, suppose, in fact, we have that for a particular A and B. So this is a little bit like the first suggestion. And I'm sorry, I didn't catch your name, but pick two numbers. So I'm gonna pick two numbers, but I'm gonna call them A and B. So this is kind of like a math course I took as a grad student, which was very theoretical. And someone said to the professor, I'm sorry, professor, this is very abstract. Can you please give an example, numerical example? And he looked at the board and he said, certainly, let A and B be numbers. So I'm going to basically do this. I'm going to pick A and B to be arbitrary. So suppose I have for some A and B, doesn't matter which one, that I have A is greater than B, but I have 1 over A is greater than equal to 1 over B, right? That would contradict, that would be the opposite. And when I do these proofs, and I should mention, we have some really good mathematicians on the staff, as you know, the UTAs and GTAs, they're amazing. I don't know if they would want to do this, but I sometimes like to take the thing that I'm putting up as a, you know, a thing that I think is actually untrue, but I'm trying to get a contradiction with a star. This comes from linguistics. If you write a sentence down, you want to analyze it, you put a star next to it saying, this isn't really English, or this isn't really Chinese, this isn't really Russian, but it shows a construction we can analyze. So by contradiction, suppose A is greater than B, but the opposite, 1 over A is greater than 1 over B. So Moses, what would happen next? What do you think I'd be able to derive from that? Or anybody? So with proofs by contradiction, we want to start out by assuming the opposite of what we're trying to prove, which is something like this. And we'll get lots more practice with this, right? This is just our second proof for this class. Yeah, so that's a good idea. I see an idea from Luke Chin. I see an idea from Dominic as well. So let me go with those ideas. I'll just do them in my own fashion, but I think basically several people kind of got this. So let's start this. I'm going to say, I'll say 0 is greater than 1 over B minus 1 over A, right? All I do is move it to the other side like that. And now I'll take the suggestion that was given, just multiply both sides by AB. So here's AB, 1 over B minus 1 over A, like that. And we can simplify this to A minus B. But then we get that B is greater than equal to A. This is a contradiction because it directly contradicts our assumption here, right? All right, so when we have this, we don't write 2 lines like we did here to say the end of proof. What we do is you write this. That means we've completed a proof by contradiction. So now this theorem is, this little claim is proven. Now, some tips. If you use these, you'll be signalizing that you're a mathematician. It's a shibboleth for saying, I'm doing mathematics, I'm at least claiming something mathematical. There are 2 ways of doing this. I like to draw a single line and then crosses through it. You could also do 2 arrows like this, but the problem is they might not meet and you don't really have a contradiction. So I like to write these like that. So this is your symbol for contradiction. This is your symbol for proof. All right, very good. Excellent job participating in what's going on in the class. Appreciate it. Any questions on either of these simple proofs? And do you feel generally comfortable with this as a starting place for the kind of proofs we're going to be doing? This is kind of a way of saying we're going to be doing a lot of proofs because they're about our programs. We want to know that those proofs are good and we can write them. Our programs are correct. Our suppositions are correct. So I'd like to know if you have any questions about what I've done, or is it relatively straightforward? All right. So I see there are a few questions, but I'm allowed a little bit of time here just to summarize. And then what I would like to do, if you all don't mind, is to, I will stay around afterwards and answer questions. So the way that we'll organize this will be, I don't like to lecture over our time. We might even take breaks at certain times. I do want to have a chance to give a little summary in the last couple of minutes here, say what I want to emphasize. I will stay around in the Zoom room here and take questions from you. You could talk to me about what you'd like to chat about. That will be distinct from another time that I will arrange in order to talk possibly one-on-one. That probably will be a more traditional office hours thing with a waiting room. In addition, every TA will have office hours. We hope to have some kind of office hours every day of the week, but your main contact with me will be the lectures. So if you have more questions and you don't mind talking in a Zoom setting where other people might hear you and maybe even benefit from the discussion, please stick around after 4:45 if you'd like and ask me questions. Again, we did a lot today. We got oriented. The main points I wanted to make in this lecture about the actual content of the course rather than mechanics were that really what we're doing is studying computational processes in a particular language, which is closely tied to the mathematics, namely Lambda Calculus. And there are two parts. There's this declarative part, which is the what is description, or if you will, math, pure math. And then there's the algorithmic part, which is how to do a description. It might be code. In some other classes, it's pseudocode. In this class, it almost always is code. The language is super simple, which means we can prove things about it. Uniform evaluation rules. Thing to do is at the front, then operands 1, 2, 3 to n, follow it, except for a very few special forms like define, which we need because we don't know what the names are. And these things together are a reification of the so-called Lambda Calculus, which is this totally powerful technique. And what this is going to allow us to do is by lecture 13, not only can I show you MapReduce and Hadoop, but I can also prove for you, and you can verify the proof, the Alan Turing's halting theorem, which is the single deepest result mathematically in computer science. And this is usually a high point of the class, although there are other high points later on. So this is a form of mathematical logic that's very useful for reasoning about functional programs and even other programs. Finally, I do want to mention that we had this notion that we could name things and have abstraction. That'll be a theme throughout the class as well. Abstraction is more or less unique to computer science and to mathematics. It doesn't occur much in the life sciences, a little bit in physics, and we're going to use our techniques to try to really understand these ways of abstracting and writing good code. So abstraction plus Lambda Calculus is a great way for thinking about complex things, structuring code, structuring ideas, and this is really a course about mathematical techniques for doing that. With that having been said, we're at the end of our time. And so I'd like to thank you all for attending. I'll see you again on Wednesday, and also we'll be interacting on Piazza. Please ask questions on Piazza. We're also happy to take comments during office hours. And with that, I will say that's the end of the lecture. And I'll stick around if you have more questions. Please reach out by chat or by speaking up, and I'm happy to talk more.
Thank you.
Thank you. It's great to meet you all. We're going to stop the recording now, and hopefully this will work, and I'll put this up for everybody.